Google Cloud Platform meetup here. Really, really thrilled to have Fractal to sponsor pizza and the venue. And so I've been friends with Ross and some of the people at Fractal for some time. They used to hang around here a few blocks that way, and they're really good software practitioners who really practice the art of extreme programming. So, I'll let Ross talk about like what the company does, the methodology behind it, and stuff like that. And thank you for coming. So today we're going to talk about two things, right? Everyone's been talking about cloud native these days. So what that means is containers as a unit of deployment, and Kubernetes, a way to orchestrate containers and running it in the cloud. So we're going to talk about that today. And I think we have started, like the last few GCP meetup has been pretty good. We're finally getting back to swing of things and organizing meetups. So really pleased that the next meetup, we're gonna be talking about, finally, about machine learning. And Chris, who's sitting over there, he's gonna be one of the speakers, and his company, Flow Technologies, which is a company that focuses on water management IoT solution, will be sponsoring that meetup. So we'll be making the announcement really soon. We also have a Google representative coming. We might have some updates on products. So we'll, between the two talks, we'll have him up and talk about any updates. So I'd like to get Ross to come up here and say a few words. Do you have anything?
Thanks, Sam. Yeah, so everybody, thanks for coming out to the Google meetup. This is our first ever meetup hosted here at Fractal. We've only been here for less than a month. So I think the big learning is that we're going to have to figure out something for event seating. So thanks for bearing with us. But they're Aeron chairs, so they should be comfortable. So here at Fractal, we are devoted to software development excellence. We consult for lots of different companies, everything from startups to large enterprises, helping them build and release software, and also helping them build their own software cultures and improve those cultures. So for us, it's all about building great software to create a better future, and building a great experience for software developers in that future. That's what we're all about.
Are you guys hiring?
We are, yes, we're always hiring. So yeah, specifically, I won't get too specific, but yeah, basically software developers, designers, and product managers are our jam.
Anyone else? Do you have any announcement you'd like to make? Anyone hiring? Or my company's hiring. I'm looking for an intern, DevOps or backend, specifically Golang backend. So, anyone else?
Not hiring per se. It's a AppSec Application Security Conference at the beach, Annenberg House, starting on the 21st with 1 day of training, 3 days of conference, very popular. I hope they're not sold out yet. They're very popular, they're very good quality without security, and specifically for applications, totally nonprofit. All the money is invested in the program. They offer heavily discounted tickets for students. Veterans can get free tickets, and the food and the venue is super at PCH right in Santa Monica. If you're interested in security, that's the place to go that I recommend.
This is January 21st?
21st to 24.
What's it called?
AppSec, California. Right. Right.
Anyone else?
Yes.
I have of a boring announcement. For anyone who came in late, keys are required for the restrooms, which are actually out by the elevator. The keys are hiding on the shelf by the laptop here. If you take one, please bring it back. We have limited copies, but there they are.
I'll put it here.
The men's room is blue. The ladies' room is gold.
Right. All right. So, anyone else? Any announcement? Not. All right. Let's start. So the first talk I'm going to talk about Docker. Docker container, they're kind of synonymous with each other. And these days, regardless of whether you're using AWS, Azure, Google Cloud, you hear this word cloud native, right? So I think cloud native, there are many different definitions, but to me I think it's really the ability to scale massively. And part of that scalability is the ability to deploy your application as a container. Why that is important is because you can isolate the application and then put it out in the infrastructure, and we'll go through that. It's essentially one of the building blocks of cloud native apps. So let's talk about software deployment in the past. So remember these floppy disks? The irony to this is that this guy actually stores more information than this guy. So the smaller you go, the more capacity it packs. So that's kind of in the past, and really software deployment is actually hard. I mean, there are different requirements that you need to do. Maintaining the code in different languages, you have to test them to make sure that they're reliable. There's no regression introduced that will break what was working before, and yet the new changes that you made needs to be tested to make sure it works. And if it doesn't work, you have to revert it back, and then you have to host it in different infrastructure and cloud providers. And then you have different configuration, different environments that you have to contend with. So it is hard, no doubt about that. But at the same time, tools are actually getting better. And there are really some great tools out there for deployment. And so before we jump into deployment, let's talk about infrastructure. I mean, specifically the definition of infrastructure. So really interestingly today, when people talk about infrastructure, at least in the realm of software development, software architecture, it is an abstraction. In the past, hardware is really your laptop, your server, your what you call the metal blade, blade metal, but today, infrastructure is really an abstract term. It can be your metal, it can be your laptop, it can even be your mobile device, and it can also be your cloud, the cloud that you rent from the cloud providers or the company that you work with that may have a data center. But there's a server, but it is hidden from you. So really these days when you talk about infrastructure, it's just a hardware somewhere that's a server and you just deploy to it. So that's really the distinction, and each year that is getting more and more abstract. And so now that we have defined what infrastructure or hardware is, how do you run an application? So this kind of goes back to computer science 101, specifically operating system, right? So you have many different layers for an operating system, right? The whole thing here is the system is divided into 4 layers. At the bottommost layer, hardware infrastructure, and then you have the kernel. You have the operating system and the application. This is pretty much like the abstract layer that you learn from computer science, right? Operating system. And traditionally, you have a single host, and in a multitasking environment, you have more than one app running at the same time, and that a lot of these apps, because to save space, and they rely on runtime libraries like the CLib and SSL and stuff like OpenSSL and stuff like that. And so in addition to application, you also have like runtime libraries that sit on top of the operating system. You have the kernel that does system call and interact directly with the infrastructure. And this is how a single host looks like. And then you have something called virtual machine, right? Like your EC2 instances, those are virtual machine. Your GCE instances, those are virtual machine. What virtual machine really is that, you know, you now have a host, but in that host you can run multiple operating system on top of that. And what's interesting is that you're really replicating an operating system and it's completely isolated from each other. So this app would not see the app is running in this virtual machine and so forth. They're completely isolated. They all have their own kernel, the guest OS, the runtime libraries and so forth. And they all sit on top of a host operating system and infrastructure. You have the hypervisor, which is kind of an essential technology that is available in the CPU to provide that virtual runtime for hosting multiple VMs. So this is really what set the computer infrastructure that we see today. The cloud is because of the ability to run virtual machine in hardware. And then you have containers, right? So a lot of times, like the distinction between a container and a virtual machine is where the kernel is. As you can see from the previous, with a virtual machine, the kernel is isolated within the virtual machine itself, and so you have to run the kernel in the virtual machine. Whereas in a container, the kernel is actually shared across all the virtual spaces. And so it's not as isolated as a virtual machine, but it's definitely more lightweight and definitely more resource efficient. And you can run a base OS on top of that, and that base OS with the container runtime will interact directly with the kernel of your host. So that's really the most fundamental distinction between a container and a virtual machine, is the kernel is shared in the hardware. So now that you have containers, really like where does container fits in, right? Is container a host, a server, or is it more like a process? So it really depends on the context. Because sometimes, like obviously, when you run a container, you could be running a detached process, and so it really functions like a server. So you can see that as a server, and it's also running an operating system. You can go inside a container, you have a shell. So very much it's like a host, but at the same time, it's also like a process. But I think the best way to look at this, to me, is that a container offers a environment that is isolated, and so you can put all your stuff in there, your configuration, your libraries, your application, and you can put it in there. It's completely isolated, and you just run it, right? So in other words, you have like a unit of deployment, and that unit of deployment have all the configuration, all the environments that you want. You can set it, for instance, in Java, you can set it to a specific JVM, and then you have another container that contains a different app that requires a different environment. You can set that up. So in some ways, to me, it's like a process on steroids, right? It's isolated, you have that environment, and you just put it out in the infrastructure. Doesn't matter how many hardware nodes it has, you run it and it's gonna execute. So that's the state of the distributed system cloud environment that we have today is this. So let's take a closer look at Docker. And really, the container technology is nothing new. Container actually existed for years. Google has been using their own containers, and all major distribution of Unix and Linux have their own containers. BSD they have their own containers, and in open source you have different flavors of containers. Solaris has its own container. Remember that? There's also and now there's actually a really good alternative to Docker is RKT. So there are different flavors of containers out there, and containers have existed for years. But then one day, about I think 4 years ago, there's this nifty company called Docker, the company. They figured a really clever way of packaging all the tools for building containers, right? And they add a really nice tool set around it, and kind of the rest is history. And so, what is Docker? Docker is just another implementation of container, and today's by far the most popular container. So I guess Docker has won the container wars. And certainly, like, if you go out there, like, all major cloud providers, including Google, support Docker. So it's a container implementation. What are the benefits? Like I said, containers are pretty lightweight. Kernel is shared, and so it's pretty resource efficient. And it's also faster to launch. You also get the isolation that you get in a VM. Not as isolated as a VM, but it's pretty close. And container technology is also improving with pretty widespread adoption. You can also very easily define and set up a container via code. So you heard of infrastructure as code. So definitely Docker falls into that, because you now have to code in order to set up your container, deploy your application. So that's what Docker is, just another implementation of containers. So Docker runs on Linux only, and it only runs on Linux 64-bit, and it's dependent on a low-level library called libcontainer, and this libcontainer is responsible for the file system, process, network within the container. Docker uses something called layered file system. So every time, like when you define your Docker containers, you have each statement that you define in your Docker file. Each statement represents a layer. And so the beauty of this is that because you can build your containers incrementally, you can very easily just peel and just add on a new layer on top of the container. So the benefits of this is that you have versioning and you have portability. We'll come back to this Linux x86 later, because you'll be wondering, like, why am I running Docker on my Windows and Mac? And we'll go through that. There's a little bit of magic behind the scenes on that thing. So if you have to walk away tonight, and this is really the diagram that you should know. Okay, so this is the Docker workflow. Really, the 4 commands that you should be aware of with Docker is Docker build, Docker pull, Docker push, and Docker run, right? So let's get the terminology right. So there are really 3 constructs in the whole Docker land. You have the Docker file that really define how your container should run and what are the environments configuration that you have. Everything, all your code is defined in this file called Docker file, right? And then you have the image. The image is, this is a built image that is, you built it because you want to compile your setting, your configuration into an image that contains the operating system, the configuration that it has, and so that when this image could be used to be executed and be run in the infrastructure. And when you're running the image, you call that a container. A container is really a runtime environment for Docker. So there are 3 different constructs, and to get from this state to this, you have all these different commands. So Docker build will build a Docker file and turn it into an image. And once you have an image, you run Docker run to execute the Docker image. And Docker, because it also offers versioning and a way for you to store different images in a registry. You have the registry where all these images are stored. It's similar to Git, where you have pull and push, where you could pull an image from a registry, and you can also push a built image into the registry. And then we'll talk about different type of registry. There's obviously public and private. You don't want your private Docker file that contains sensitive information to be published to a public registry. But again, end of the day, these are the constructs for Docker, and these are the 3 primary commands that you should be aware in order to be proficient with Docker. So as you have public and private Docker registries. So again, registry is a collection of Docker images that you put on the public space or private space that you can pull Docker images from to run. So when you push, you need to have write access. Even if you push a Docker image to a public registry, you have to have an account. So Docker, the company, they have a public registry it's the standard for all Docker images. So if you're gonna pull an official image, say Nginx, there is the official Nginx public Docker image that is hosted on hub.docker.com. You can obviously have your own Docker that you define and customize. And when you have built that Docker image, you can push it out to the public registry to share with the rest of the world. In order to do that, you need to have an account, and you have to log in order for you to push it to the public registry. Now, you also have you can also, with all the cloud providers out there, including Google, and Google is called GCR, Google Cloud Registry. It has its own private registry that is only you, the project owner, and anyone that is part of that project can have access to. Obviously, you also have to provide the access to whoever needs to have access to that registry, but it's yours and can define who have access to that. And every GCP project has a GCR associated with that. And you would use gcloud, the command line, to set it up for you to log in to get authorized access to the GCR registry. And so one thing to be careful with is that by default, Docker pushes the local image to the public repository. You want to be a little bit careful with that to make sure that your context for your Docker is not, so when you're working with your sensitive private image, you want to be careful that you're not pointing to the public registry and then you inadvertently push that image to the public space. So be a little bit careful with that. I think there's a lot of things that are built in now to prevent that from happening. But I think in the early days, it's not a big issue, but just be careful with that. So going back, we're going to talk a little bit about the Docker image and the layered file system. So as I mentioned before, at the very low level, you have the kernel and you have some very low level libraries that's available on the host infrastructure. And then you have what you call a base image. Docker always start with you defining what that base image is. So typically the base image will be like one of your Linux distro, like Ubuntu, Alpine, BusyBox, and so forth. So you're gonna define your base image, and then you're gonna add like your configuration, you're gonna add your binaries on top of that. Every time you add something, it doesn't replaces the layer before it, you actually add on to it. And so one thing you want to be careful too is that when you're building your images, once you place it out there, even though the layers seem like you thought you may have overwritten a layer, but it is still there and it can be accessed by people. So be a little bit careful with that. But at the same time, because all this is layered, all these different layers are actually cached in your local repository. And that's really good because you can build something really quickly. I mean, imagine every time you make a change to a Docker file and you have to go out there to download the almost like 500 megabytes of Ubuntu-based operating system. That's not very efficient. So a lot of the layers are actually cached in your local cache, and so it makes the build a lot faster. Yeah, so the implication of layering is that, for security, deleting a layer, just let's say that you have a Docker file, you have like, say 20 lines of configuration, and then you do a build, you even push it out to the registry, and then later you discover, holy shoot, I forgot to remove a sensitive data, and you go back and you delete it. Actually, that layer is still available. You can do a Docker history to see the previous history, like what you have done to the Docker file. Maybe you could retrieve information about that, and hence, if someone is malicious, they could actually retrieve sensitive information if you're not careful about that. And also, one thing is that the layering also have what you have a cascading effect. So like so each line corresponds to a layer. So the line that's on top of the Docker file, if you make that change, it's going to have a cascading effect to the subsequent line below it. So enhance the layer. So when you make the change upstream, you want to be careful because everything after that is going to be rebuilt again. And so when you're actually using a Docker file to encapsulate your application, that's why sometimes you want to run your download and installation of your packages first, rather than you compiling your code, because chances are you make more frequent changes to your source code, and so you want that to be somewhat at the bottom so that it would not affect any layer on top of it, and you can have a faster build as a result of that. So keep that in mind. So let's talk about base images sizes. So I compiled this like a long time ago. That's almost 1.5 years ago. Obviously things have changed, but in general there are different distribution of base images for Docker. There's like your usual suspect in the Linux distro land, Ubuntu, Fedora, Debian, Alpine, and BusyBox. And you can see the huge discrepancy between these three distro and the more common distro. I think Ubuntu have done a pretty good job now. Like it was 188 about a year and a half ago. I think it's hovering around 120-ish now. Alpine has always been really lightweight. BusyBox, so BusyBox and Alpine are very similar. In fact, I believe Alpine is a variant of BusyBox, and they, I mean, a year and a half ago, it's hovering around 5 megs. Like now, like I think it's, you know, like things have improved and it made the footprint might even be smaller. So keep this in mind when you are building a Docker image. Selecting the base image matters because of the size. And I'll show you like how you can actually reduce the size of your Docker image, and that will help you in reducing the size. And also, for security measure, like when you're installing a Docker image with a big base OS, you have to ask yourself, do you really need some of the additional things that you need? So there's an art of selecting the right base image, ordering your configuration, all of that have some implication. But you know, if you're starting out, I wouldn't be too worried about all of this. You know, just get a sense of like how you do it, and then when finally you're ready for production, you can always like do the necessary steps to harden your OS to improve the reliability and stuff like that.
I think you just say Docker running on Linux only, but how can you run on the Mac? Is it you run on a Mac
Yes.
BSD?
So this is where we're getting at. So how can you run Docker on the Mac? So you cannot run Docker directly on the Mac. That's the thing, because Docker can only run on Linux and it has to be 64-bit Linux. So on your Windows,
on the BSD, because a Mac is based on BSD.
so yes, so there are two ways to run Docker on the Mac, and it has to go through the emulator. So for like, there are really two options of running Docker on the Mac. There is something called like Docker Desktop and then Docker Toolbox. So funny thing is that I started talking about Docker a year and a half ago. I have a set of slides that I prepared a year and a half ago. And 2 nights ago when I was preparing for this talk, I looked at the slides and I was like, oh wow, a lot of the information on this slide is pretty outdated now, because a lot of things have changed in the past 18 months. When 3 years ago, Docker Toolbox was the dominant tool for running Docker on the Mac. Essentially, you are spinning up a virtual box behind the scene, and that virtual box is running a Linux operating system, boot to Docker. Remember that? So it's running boot to Docker on a virtual box, and then with that, what happens is, so this is the Docker Toolbox on the Mac. So you have a virtual machine, virtual box, and you're running Linux on top of it. So your Docker is really running on a Linux that's running on the virtual machine that's running on Mac OS. And then in your shell, so Docker, the company, does a pretty good job in hiding a lot of this from the user, but they also provide really good tools that you can just use the shell and then issue commands like you would on an actual Linux machine. So to the user, they think that they're actually running Docker on the Mac, but behind the scenes is really running it on, the Docker is running on the virtual machine, and through the Docker engine in the virtual machine, you have the API that interacts with the command line on your Mac. And so it appears that it's running on the Mac, but it's not. So there are really two flavors of running Docker on Mac. So this is like the old way of running it, but about a year ago, Docker released something called the Docker Desktop. And it's actually pretty cool. So instead of VirtualBox, they're actually using, the Mac OS has a low-level framework called Hypervisor. So Hypervisor is it's like a, not exactly an emulator, but a way for Mac to run virtual spaces, a virtualizer, sort of. And then it uses a Alpine as the base OS. And so these days, if you're using the Mac, you're using Windows, just use Docker Desktop. Docker Desktop also have a lot of the new features that Docker, the company, introduced come out in Docker Desktop before Docker Toolbox. I don't even think this is really maintained anymore. And also Docker Desktop supports Kubernetes. So running Kubernetes, you have two ways to do it locally. You have Minikube, or you can use Docker Desktop, but Liam will cover that. And also the GUI is pretty nice. Sometimes, like, if you're comfortable with the shell, go ahead. Use Docker, the command line, and just spin up something. But Docker Desktop has some very cool GUI that you can use, and it's really nice. So I would say if you're starting out, just use Docker Desktop. It's a lot easier, it's more powerful, and it also supports a lot of the newer features, including Kubernetes on the Mac and Windows. So yeah, to download, I've included instruction on the slide. I'm going to share with the group, and you can download it. So, this is okay. So that was the introduction, a kind of a quick primer for Docker. And I know that there are probably some very people who use Docker on a day-to-day basis. So I've also included some tips and tricks. By no means I'm an expert, but so if you guys have any additional tips that you'd like to share, feel free to raise your hands and tell the team, or contradict me if you want. If I have something wrong, please tell me, because I'm learning too. I'm learning about tricks every day. For instance, I learned about Docker Stack today in a way that you can define your Docker, you can run your Docker Compose file in Kubernetes by using Docker Stack. That's amazing. But then I have to learn another new set of commands or subcommands, all right. So first tip, use Docker Compose. It's awesome because there's these days there's just too many command programs, too many CLI programs, too many commands, too many subcommands. I often just confuse between Git and Go, kubectl and gcloud. After you've done that, it gets really confusing. So I couldn't remember all the different flags, different arguments, sometimes you have to use double dashes, and sometimes you have to use single dash. Screw this. So the best way to do is to encapsulate all these arguments into a file, and call that file dockercompose.yaml. And you just define everything there, and it's super simple. You have everything defined in that file. You just run docker-compose up, build, down. That's it. Everything is defined in the file. I mean, the downside to it, obviously, is that when you're using a CI/CD, when you have to pass the arguments, it's better to just use this so that you can script it and just pass but even then, you can have templating solution that you can pass it to the Docker. But do this, it's super simple. You just put everything in a file, and then you will not forget Docker Compose up, Docker Compose down, Docker Compose build, done, simple. And then you can really focus on what you like to do best, coding or or whatever. I'm not a DevOps guy. I'm a software developer, so I'd rather be coding than dealing with Docker. But sometimes it's pretty fun. So one of the things is that you can use, and one really nifty application of Docker Compose is that you can use it for build. So you can use it for build. For instance, you can pass like arguments into the Docker, and you can just pass. You can define it in your file, and then you can just run Docker Compose, and everything is encapsulated here. It's really a good use case for that. Tip number 2, I love to mount local files and directories. And then, so the thing is that, as you recall from many slides ago, is that a Docker container is pretty isolated, right? So what you have a Docker container running, what if you have your files that you need to mount, you need to share the Docker container, I can do what you call a mount bind, where you mount the local file or directories, and you mount it into a container, and then when you spin up that container, the container will see that file. And this is super, super useful, because how many of you here use like NVM or Node env? It's a language versioning manager. So sometimes like, oh, I need to use the latest and greatest Node version 12. But then you have like an app that's legacy and it only uses like Node 8. You would use this version manager to switch between different versions. You have that for Ruby, Python, Go, etc. So, but the problem with that is that you have to download this version manager. You have to install it, and then you have to install the version and stuff. So now that you have Docker, you can really leverage Docker, right? Because you can have a container running, say, Node version 12. You can also have another container running version 8. And then what you do is that you mount the directory containing your source, and you just use the node in your container to run against the source directory that you mounted to that container. So this way you can have multiple containers representing different version of your language, and you just run it that way. So it is pretty cool. Also, when you mount a volume, there are images out there like databases that allows you to inject a configuration when you spin up a new database. For instance, you could be spinning up Postgres, and with this Postgres, you need to set up your user and password. You may need to seed. You may need to create tables, create indexes, and then seed the data. Many of these containers, images, they offer a way for you to inject a configuration file. And so what you would do is that you actually have a configuration file in your source directory, and then you do a mount. You mount that file, and it will be visible to the container. And if you place it at a location where this program is going to scan, it'll pick it up, and then it'll do the initialization at boot up. Then another good use case for mount is that you want to persist your data. So Docker is ephemeral, right? Because it's isolated. When you spin it up, you have something, but then when you tear it down, when you tear a container down, everything inside is destroyed. So you're working on a project, you put your important files in that container. When you do a teardown, when you stop a container, remove a container, everything is lost. So a good way to do this, especially for databases, is that you mount a local directory where the data file for the database contains. So when you do tear down the database, your data is still persisted, and you wouldn't suffer any data losses with that. So this is like the full Docker Compose that combines tip 1 and tip 2. So tip number 3 is pretty interesting, because a lot of time when you run a Docker image, you expect it to work. But in real life, like most of the time, like 90% of the time, things doesn't work. So like, what the F, right? So in EC2, in VMs, you can just SSH into that VM instance, and then you can go into like, look at the logs, run your script to see if it even works, and so forth. So a Docker container in some ways is like a virtual machine, right? It has a shell. But you don't SSH in there because there's no SSH. But Docker provides a command call exec, and you give it the correct parameters. You tell it what running container, it has to be running though, a running container, and then you have the command to run. So typically, you would just run bin/bash or shell. You go in there, and then you just like start using a command line, just probe around and so forth. So it's pretty useful. Another really useful thing is that a lot of time when you're running a database, you also want to go inside the database to get it's a console for the database. Instead of downloading and installing the client program, you can just do an exec into the database container. Typically, like 95% of the time, a database server container would also have client programs and tools available. So you just go inside the container and just run the client tool to go inside your database. So another good tip, like it's really, really useful, and I don't have to install anything on my client. Like these days, I just Docker this, Docker that. Life has become somewhat easier. So this is actually pretty important. So when you start to build your Docker images for production, you seriously want to consider multi-stage build. You can have one Docker file with one single build, meaning that you put everything in there, you build so a typical case is that you have your source code representing your project. You have to build it, meaning you have to install your packages, you have to run tests, you have to build, and then you have to package that, you have to copy stuff over. You can do that in one single stage. Or you can break them down into multiple stages. So essentially, you have your build stage. After you have done your testing, your package install, you have an artifact, you copy that artifact into your final container image, and you deploy that container image. So one of the biggest advantage of multi-stage build is that it drastically reduced the size of your Docker image. So I have my app written in Golang, and I tried this 2 nights ago just for fun. So it's single stage built with Ubuntu. My final image size for the final image came out to be 880 megs. So I said, all right, let's go to Alpine, right? Because it has a pretty low footprint. And the final build is 382, not too shabby, it's half the size of Ubuntu. And then I did the multi-build, and I got it down
looks
to...
like you have a typo.
You think you have a typo. I think you flipped your tab.
Multi and single are switched.
Oh, sorry, this is multi, so yes, I indeed have a typo, thank you.
Sure.
So this is multi, it
Because
reduced
I was getting confused. What's going on?
Yes, this is, this is single, this is multi.
Yeah.
So,
Switch those.
flip. So, so using Alpine and multi-stage build for my app, I finally got it down to 15 megs. So from 880 megs down to 15, that is a huge reduction. Now, obviously, there's some caveat. Obviously, this is Alpine, that's Ubuntu. But even if you use Ubuntu multi-stage build, you have reduced from 880 down to
Yeah.
almost 100. That's a big reduction. And typically you also want to use multi-stage for better security practices. So it's great. And here it's like essentially, so this is the Docker file. You have two stages. The first stage is really a simple build, right? For Go, this is a pretty straightforward project because there's no third-party dependency. So I just do like a Go build, bang, I have the artifact or the binary. And then the second stage is that I'm starting from fresh. I'm using the base image Alpine, and I always add a user that's not root so that you run it in a non-privileged mode, nobody. And then from here, copy what you have built in stage 1 to stage 2, and then you just run it, expose it, the port, and you run it. So really a pretty good way. And later I'll show you how I reduce it from 15 down to 7. It's even more, there's more tuning to do. So the thing with Docker is that it can be, yes, when you run a lot of Docker containers in your machine, especially with a MacBook that's 5 years old with 16 gig, when is Apple going to build MacBook that's more than 16 gig? Yeah, so you want to have a way to kind of constantly check the resources that are consumed for Docker. So here are some of the most commonly used Docker command. Docker images or Docker image ls, singular, will list all the local images. It's pretty good. Actually, Docker stats is pretty cool. You can see like the stats, CPU consumed, memory, and stuff like that is pretty cool. But this is the best, like the mother of all housekeeping command is Docker system prune -a volume. So what this does is that it will delete all stop containers. So in Docker, when you spin up a Docker container, you just issue the command run, right? It will just spin something up. But when you tear it down, it's actually a two-step process. You have stop and you have remove. So after you stop a container, it's actually suspended in its execution. You have to remove the container. So doing this will remove like all stop containers. And there's also like dangling images. So what that means is that sometimes you do some build, you halfway through it, you interrupt it, and it dangle, right? There's some caches left. So this, when you issue this command, it will remove a lot of the access resources that's being held up, and you free up your memory. It's pretty awesome. By the way, I will send this out to the group, so yeah, don't worry about it. This is not a great tip, but I thought it might be helpful because if you want to transfer a container to another host, the container has a snapshot of the state that it's executing. So to do that, you can just stop your container, commit it to your local images so that you have a backup. And then from there, you just save it, bar it, and then you transfer that file over and you do a load. And now you have a Docker somewhere else. Pretty straightforward. So this is interesting. So Docker file to me, like, it reminds me a lot about scripting, even though it is more of a declarative way of writing. It's not really a script because script is very procedural. A Docker file is you declare the state that you want in that file, and then you pass that file to Docker. It will just, spin up an environment that you have to find in your Docker file. But the point I'm trying to make is that sometimes you're repeating the same value all over in your Docker file. And sometimes you also want the ability to inject values into your Docker file. So the Docker file commands are ARG and env are pretty good ways of passing values to your Docker file. And you use the Docker file to do two things, right? You use the Docker file to build, and you use the Docker file to also run the container, because the images is based on what you've defined in your Docker file. So when you run your image, like by extension, you're running your Docker file. So there are some nuances with env and ang. So essentially, Arc is something that you can use to inject build time values. You just inject it here. When you build an image, it will read that value. It will, put it into your build process, and you have your image that uses those values. Your environment is more. It starts from. So environment is definitely more runtime. So when you run your image, you have the underlying application. The application could just pull and extract the environment variable. So it's definitely a runtime thing. So so it can utilize like both of this. There's some nuances where the Arc, like after build, is not available for running. In your Docker file, you have a command called entry point. Entry point is a run. Entry point and run. Sorry, not entry. Entry point and command are commands that are executed at runtime. So you cannot pass your Arc into an entry point and command because it no longer exists. Like the Arc will unset itself after you have built the image. So you have to use an env for that. So and also there's a trick to do this, because Arc is no longer available at runtime, but you can still pass the value from Arc to env by using this trick here, where you assign the Arc variable to this value, you then could assign this value to the env, and then at runtime, this will be interpreted as an environment variable in the Docker container. So, and tip number 8, harden your container. Don't run as a root. So always use that command user to run your Docker container. I mean, when you run it as a root, if you're attacked, your process runs as a root, it's a privileged mode, it can gain access to the kernel, and you don't want that. And in Unix, TCP ports 1024 and below are privileged port. You have to be root to run them. So because of that, like, you don't want to assign a port number that is below 1024, and that's why typically you see a lot of Docker has a port number that's above 1024, and then at runtime, or when you push it to a Kubernetes cluster, you do port mapping to map it to like 443 or 8 or 80 or something. I mean, you shouldn't even be using 80, you should be using 443 to, anyways. But yeah. Trust but verify. Use only images you trust. So the official images, like if you go into don't use a public image with 10 downloads for a production for a production container. You really can. Even if you have like a public official image, you want to, if you are extreme, you want to be careful with that. You can do pull by digest. So you have a shard 256. Every Docker image on the registry has a digest signature. So make sure you download that specific signature and go from there. one process per container. Don't, yeah, just keep it simple. Be careful with recursive copy. So when you do this, like copy ... you're really copying like everything, including the subdirectory. Be careful with that. And be careful about using Arc. You don't want to, you could be passing sensitive data, remember Docker history. Just be careful. And simpler the better. Use like minimum images that you only uses like system dependency that you need, and that's it. And so that's like hardening. That's more, but these are like the simplest practices, and if you can do this, like it's pretty good. So let's talk about extreme hardening using Scratch. So Scratch actually means no base OS, right? So everything that we covered so far, we mentioned that there's a base OS running in the container, but you actually don't have to do that. You can actually interact directly with the kernel, but there's a caveat. You can only run a compiled binary that is capable, that is statically linked, and that it can have the ability to interact directly with the kernel. And that means you're only limited to C, C++, Go, Rust, I think that's D, yes, D, that only these languages it can compile a binary, an executable that you can run directly and interact with your kernel. So yeah, because the application must be on its own and there's no dependency on any runtime. But with Go, you can easily do that. So Scratch has no base OS, but you have to do a few things with that. Alternatively, you can also use as a Google image called Distroless. It is very similar to Scratch with a few things in it. So this is what I did. So all of this is the same as before. The only two, I made two builds, one using Distroless and the other using Scratch. So for Scratch, like I got it down to 7.1 from 15.4. That's pretty good. And then with Distroless, I got to like 7.6 megabytes. So yeah, and this interacts directly with the kernel. So now, like not only do you have like a pretty secure container, you also have a pretty decently sized container as well. Okay. So yeah, essentially you have to do a two stage build. And so if you're using Go, you have to compile a binary that targets Linux and your AMD 64. You have to be very specific. So when you do a build for Go, like in order to use this in Scratch or Distroless, you really have to compile it. You have to statically link the library. And then once you have that, you're really compiling everything into one single binary. And that binary, you copy it over to your final image and you deploy that image. So there are a few things that you actually need. You cannot just put, well, you can, but it's actually useful to have, if you're using any SSL, you need to have your CA certificate. Time zone is actually pretty useful for timestamp parsing and stuff like that. You also don't want to run it as roots, and so you have to create a user and then copy the password and group over to the final build. So there's a little bit of an extra step to copy some of the system dependencies. So it's not completely Scratch. So you have to copy some of the binaries over. And so as an alternative, I'm suggesting instead of doing that all by yourself, Google already provide a Docker image called Distroless. Use Distroless. It's awesome because you have like all of this defined, which is similar, and then you don't have to set up the dependency yourself. You just compile your like Rust or Go into a statically linked Linux x86 targeted binary and just copy it over and just run it. It ran, it's fast and it's secure, so pretty happy with that. And so, yeah, so I'm gonna start, this is like the last section, running multiple containers. So, the use cases that in real world production application, they're multi-tier, right? You have like a web application running the API service, say in Golang. And then you have your data store. You have your Redis, say for caching, and you have it to save your user sessions. And then you have Postgres as your core data store. So you kind of have to run these three containers. You have to orchestrate them to run it as a group for them to talk to each other. So how do you do that? You know, you can. This is where I messed up. I forgot to copy one of the. So, in the past, like 2 years ago, Docker volume is still pretty useful for the reason I mentioned, but these days we don't use Docker volume for sharing information between different containers. You can also have like Docker linking and Docker port mapping. They're kind of like really old ways of doing that. You can still do that, but these days you have better tools. You also have better support for Docker Compose and Docker Swarm and Kubernetes. Those are like much better way of doing things. And these days, like Docker even support Kubernetes. So, you know, like I remember like a year to 2 years ago, there's like huge battle between Docker Swarm, Kubernetes, and Meso. It's just really like confusing. But I think these days, like Kubernetes pretty much like won the orchestration war. But now there's more. Now we're talking about like service mesh and stuff like that. But that's for a different topic. So put it this way. So when you're running multiple containers, I think before like, you know, the setup is that you download Postgres and Redis, you know, both the server and the client programs into your workstation, install them, set them up. Probably you're gonna cut and paste instruction from some README to set them up. And then depending on the project, you may have a dev environment that is remote. You ask ops to spin up a VM instance, set up an environment there, make sure no one else is using the environment, ensure that the setting in your local environment is the same as your remote dev environment. It's a lot of work. That's before. A better setup for local environment, which is the last tip, is that you Dockerize everything. Just Dockerize everything, right? So your app that you're writing, put in a Docker file. The databases that you depend on, Postgres, put in a Docker file. You don't even need to put in a Docker file. You could put in a Docker Compose and just pull the image from the public registry, configure it. You don't even need to write a Docker file. You have the Redis, the same thing, point it to a public image, pull it, configure it, run it. So now you have two ways to orchestrate your multiple containers. So for local run, just use Docker Compose. It's super, super, super easy. You don't have to deal with like service, pods, blah, blah, blah. Just one Docker Compose. And it's also pretty efficient. It's great for a single node run, like your workstation. Just put everything in your Docker Compose, define all your services, Docker build, Docker up, Docker down, done. And then once you're like closer to release date, when you need to start to test against your environment, that's when you write your Kubernetes manifest files, and then you just deploy into a Kubernetes cluster that is defined for you. So with that, I've included like an example of a Docker Compose that encapsulates like the 3 different containers. And yeah, I think you probably have better ways of writing this, but this is just a sample. And so with that, I'm gonna extend like this cheat sheet to include infrastructure and Kubernetes. So with that, thank you for your time. And yeah.